Greetings and welcome back. So, where are we in the course? We're now talking about what I've entitled active matter, which is probably a little too narrow actually for what I had in mind for this section of the course. But what it is it's the entirety of the ideas that surround what makes the elements of the periodic table when they're configured in a living organism behave so differently than in a piece of steel or in a piece of granite, like at Half Dome in Yosemite or something like that. And it's for sure true that the subject of what is now called active matter within the physics, biophysics, and biology communities is a part of that, and actually a wonderful part of that. Again, I'm thinking of it as being sort of a more broad subject than that. So specifically, what we're doing is we're setting up the machinery of field theories, and I've already talked about stress and strain. I gave you some background on field theories, and I gave a first discussion of elasticity. And now what we're going to do is we're going to do the elastic theory of beams. So that's our topic for this vignette is the elastic theory of beams. And this is really a very beautiful and simple idea, and it also represents one of my favorite themes, which is coarse graining, which is, how do you start with a complicated thing like a material, and which, as I show you in this figure, the material is made up of atoms ultimately, like I could go to that level, and these atoms are effectively connected by springs. And the reason I say that is because there's interactions between the atoms, and when the material is in mechanical equilibrium, then the interaction between the atoms is quadratic for small displacements. In other words, for small departures from that equilibrium state, the potential energy landscape will be quadratic, and that's the nature of expanding around a minimum. So, and that's a very deep thing that I mentioned earlier in the term. So what we're going to do is we're going to think about how to parlay our understanding of the sort of atomic level action, which is telling us, atomic at the microscopic level. I guess what I would say is the microscopic level. We know that we have, a force between atoms somehow of this variety. So this is near equilibrium, and it's very important that I make that proviso because more generally, if I were to draw the potential energy, and it doesn't even have to be radial like this, but it would have some form like this. So this is a V of r. In principle, there could be angular interactions and so on. So anyway, near equilibrium, that is to say, when I'm in this neighborhood right here, this thing behaves quadratically. And if that energy behaves quadratically, then that means the forces are linear in the displacement, which is what I wrote right here. Right? Okay, so and further, what we're going to do is we're going to exploit the one-dimensional Hooke's law. And what I mean by that is that I told you the other day that in the one-dimensional incarnation, we can write the force per unit area. So this was, you'll recall, the stress, and this was the strain. I can write things in that language, or I can say that there's a strain energy density. So I'm going to refer to this as the strain energy density. And the strain energy density is going to be given by 1/2, and then the Young's modulus, and then delta L over L squared. So let's look at the units. First of all, the strain piece, which is this part, the strain piece is dimensionless. This bit, you'll recall, is measured often in gigapascals, which is newtons per meter squared, yes. Or alternatively, I can write it as joules per meter cubed. So it's an energy density. So that's the reason I'm referring to this as a strain energy density. And the picture that I want you to imagine is that I have my continuum mechanics potato, and somewhere inside of that potato, I've queried about how much energy is stored. So this is a material volume element, I'll call it, in following the convention in the field. And so the energy in this little element, energy due to strain, elastic strain, let's be precise, energy due to elastic strain in this little volume element is given by 1/2 E delta L over L if I just pulled it in one direction, delta X, delta Y, delta Z. Okay, I'm being very limited in the scope of the kinds of strains that I'm imagining, because I'm imagining that this thing has been solicited by only a one-dimensional load, which leads to a one-dimensional strain. Okay, in other words, I haven't pulled it in all three directions. I've just pulled it in one direction, so it's elongated, and that's the reason I can get away with this simplified form of the energy. So I want to point out, so we're thinking about the elastic theory of beams, and I want to note that beams can be stretched, they can be bent, they can be twisted. And all three of those states of deformation result in an elastic strain energy. And what I'm going to do is I'm going to focus on this particular configuration, which is beam bending. So now we're ready to actually get to work. So the goal here is to compute the strain energy of an elastic beam. And just to foreshadow why I would care about such a thing, let me show you these amazing, beautiful structures. What you see on the left, this is from the work of Tabin and Mahadevan. I think the first author is Savin. I think Amy Shire is on this paper. This is Nature, maybe 2012 or something like that. I'm not sure what year. And this is one of my, really, I have to say, one of my favorite papers. I don't know, that I've read in my career in biophysics. It's an exquisite paper from the standpoint of the experiments and the care that needed to be taken to actually then make the theory experiment dialogue work. And all I really want to say is that one can ask the question, what's the nature of the structure that's formed in the gut, which is what's shown on the left here. So this is gut folding, you know. And what I'm going to claim, in fact, again, just to foreshadow, here's the whole reason that I'm going through this is I want to be able to do this calculation. And the calculation is illustrated beautifully by a little material analog that they constructed and showed in their paper, which is to say, as you can see over here, they took some elastic tubing, that's this part, and what they did is they sewed it to a piece of rubber sheet. So what they have is they have a tube and they have a sheet, and they sew them together, but they've stretched them differentially. What I mean by that is that they're not stretched to the same extent when they're glued together. This should make you think, perhaps, for example, of the famed bimetallic strip, where if I take two metals and I put them together and then I heat the system, they have different thermal expansion coefficients, and what that will do is it'll end up leading to buckling. And this is a trick that has been used historically as a feedback mechanism to make a switch, basically. So you have an instability, and this thing spontaneously buckles, and it forms a structure like this. This is actually what happened when they sewed the tube onto the rubber sheet and let it relax. So I'm going to talk about all this, but in order to talk about it, we're basically going to calculate the strain energy associated with the bending, which you see here, and the stretching of this sheet. And to do those two things, I need to get us to the point that we understand this equation. So that's the point of the remainder of this vignette. I want to be able to understand where that energy comes from. So the first order of business, one, is kinematics. So kinematics refers to the geometry of motion, or the geometry of deformation. And, in a way, you could think about Galileo's famous experiments on the projectile as a bit, in a certain sense, kinematics. He was telling us about the position as a function of time without really telling us anything about the relationship to the underlying forces that cause that motion. So kinematics is about the geometry of motion. And here, what you can see is that we're going to take this beam and we're going to bend it. And we're going to bend it into this configuration. And there's a very beautiful insight, which is that there's a line, which, as you can see here in this case, is along the center, which is known as the neutral axis. And that line has its length unchanged during the deformation. Why is that important? Because this fiber, which is above the neutral axis, gets stretched. This fiber, which is below it, gets compressed. And what we're going to do to find the energy is we're going to sum up over all of these fibers, z by z by z, in other words, going up and down from the neutral axis, and we'll figure out how much each one of those is elongated, and we'll use that to in order to write down the energy. Okay, so we need to do a little bit of geometry first, since we're talking about kinematics. So what I'm going to do is I'm going to draw an arc of my beam, and here's my center line, which, as I said, has length L0, and I'm going to go up some distance z, and I'm going to be interested in the stretch of the material line elements at a height z. So the first observation I want to make is that this thing is part of an arc of a circle subtending an angle theta. And this distance right here is the radius of curvature. So I've taken the beam and I've bent it into an arc of a part of an arc of a circle, and the radius of curvature is capital R. Okay, so that means, using the definition of radian measure, that theta is given by L0 over R, and then if I go up by some amount, then I will have L of z divided by R plus z. In other words, if I go up to this distance right here, let me do this in red, this length right here is what I'm referring to as L of z, and I can always write that as L0 plus delta L of z. That's an equivalent way for us to think about it. The radius, the distance from the center of curvature of that line, is R plus z. Again, I note that z I define here is the distance away from the neutral axis. So from here, it's a matter of doing a little bit of algebra. So this tells me that L0 over R times R plus z is equal to L0 plus delta L of z. And I can rewrite this as L0 plus ZL0 over R, and that's equal to L0 plus delta L of z. And this tells me that delta L of z over L0 is equal to z over R, and this is the strain. So that's equal to epsilon of z. So we've actually characterized the geometry of deformation. We've said what the strain is everywhere within the beam, which is that's powerful. We actually have characterized the nature of deformation of this object. So now we're ready for the next step, which is to obtain the energy. How do we do that? So step 2 is to find the energy. So how should I think about that? Finding the energy. Uh-oh. I lost the connection, so please bear with me. I'm really sorry. Technical difficulties, that's part of the pandemic. What can I tell you? Okay, I have a feeling this might work. Okay, good. So we're ready to find the energy. So here's the way I want you to think about this. So I've got my beam. Oh, I've got my beam. Shoot, it kicked me out again. Waiting for my computer to connect to my iPad. I'm begging your forgiveness. The technology is super impressive, but get some glitches now and then. Okay, it's back. Let's hope. All right, so what I'm saying is that I have my neutral axis here, and I'm going to focus on a particular little volume element right here. So this volume element is at a height z off of the neutral axis. That's the first thing to say. And so the energy, the strain energy, in that little box is going to be given by 1/2 times E times Z over R quantity squared, and then times delta X, delta Y, delta Z. So that's the energy associated with this one little box right here. And if I want to find the energy associated with all the boxes, then what would I do? I would do 1/2 E, and then let me call it sum over slice. And then, well, what do I mean by a slice? What I mean is that I'm going to take this cut through the beam, and that slice is going to be equal to, it's going to be equal to the area, the cross-sectional area of the beam, and then times Z over R squared, and then delta X. And okay, so this is, I'm not sure that that's as helpful as I want it to be. So what I've done is I've integrated over the area of that plane. Yeah, no, that was a bad move. Let me strike this from the record. I don't think that's helpful the way I wrote it. Okay, let me try again. So let me be more careful about it. So there's a sum over all x's, there's a sum over all y, and there's a sum over all z. So the first strain energy that I wrote was of a material volume element. So let me get my notation right here. And what I'm trying to do now is I want to get the total strain energy. So, yeah, so what that asks me to do is it asks me to take the same expression, which uses the strain, and then delta x, delta y, and delta z. So all I've been sorry for what seems like confusion. My only confusion is how to state this in a way that is actually clarifying as opposed to obscuring the point. And the instructions given by this particular expression is it's saying visit every little cube inside of the beam. At that cube, ask it, how far are you away from the neutral axis? That's the quantity z. Find the strain there, and then multiply by the volume of that little element. So that's basically it. Now, let's convert that into an integral. So that can be rewritten as 1/2 e, and then 0 to L dx, and then, let's see, I guess I want to say here, dA, z squared, and I'm going to pull the r squared out in front. So this can be rewritten as e over 2r squared times L, and then integral z squared dA, where this is, over the cross-sectional area. Yeah, maybe I shouldn't use this notation. So this is over the cross-sectional area. Okay, let's just review. So point one, we worked out what the strain is as a function of height z from the neutral axis. And that's how we produced this quantity right here. Oops. This quantity right here. So that's a strain at height z. Then we said, well, let's find the energy. So my scheme was first to use Hooke's law to find the energy in this little cube right here, this one, which we did right here. So this is the strain energy associated with one little cubical material volume element at height z off of the neutral axis. Then I said, well, we want to find the total strain energy. How do we do that? We visit every single material volume element in the entire beam. I denoted that abstractly here with the sum, a little sloppy, just saying sum over all x, sum over all y, sum over all z. In that case, assuming that x, y, and z were discrete. And the reason I say that is because I've discretized into these material volume elements, so in principle I can identify them by a set of integral positions. Then I converted this into an integral, which said, look at all x's, and then integrate over the cross-sectional area of our beam, whatever that thing may be. And what we see is that what we're left with is what I'm now going to refer to as E times I over 2r squared times L. I is known as the areal moment of inertia. Its dimensions, so its units, are meters to the fourth power, which is interesting. Let's just see whether the units work out here. So we have E has units of joules per meter cubed, and then I has units of meters fourth, L has units of meters, and then that's divided by r squared, so E I over 2r squared L is going to have units of joules per meters cubed, meters fourth, meters divided by meters squared. Oh, man, this is really becoming a nightmare. I'm really sorry. Trying to get back. I'm not sure what's going on. Just bear with me for another minute. Okay, still trying to connect. Well, so let me keep talking while it's trying to reconnect. So what I was going to demonstrate just then is that we end up with units of joules, and so that's fine. It's claiming to be connecting, but don't know. back. Yeah, so what you can see here is that there's meters to the fifth downstairs, there's meters to the fifth upstairs, and so we're left with joules. The areal moment of inertia, I wanted to comment on that. So this is something that, what does it do? It basically notes that I is equal to the integral dA z squared. And I always like to tell people, two kind of examples, everyday life examples that might matter to you. So one of them is a bike frame on a mountain bike, for example. And you'll notice that lighter bikes have a higher diameter. And even though the weight is lower, the thing that they're doing is that they're exploiting the fact that the mechanical strength of a beam is the product of E times I. What do I mean by that? E is the statement about the material. It's telling you about how stiff the material is. That's what E represents. I, on the other hand, is a statement about the geometry of your object. And I is telling you how much of your mass is far from the neutral axis. So for example, when I have a very large diameter bike frame, all the mass is farther away from the center of the beam axis, and that gives you a larger stiffness because I is larger because of the z squared aspect. The other example that you might think of is if you're driving on the highway, you're probably used to seeing now and then a truck that is carrying I-beams. If you look at the beams from end on, then an I-beam is shaped like this. And this is just the brilliant way to exploit the z squared aspect of the beam, because here the z is the direction away from the neutral axis. And so what they're doing with these I-beams is putting as much mass as far away from the neutral axis as they can and putting as little mass as they can along the neutral axis. So this thing gives extra strength against bending, but not because you made it more massive, not because you made the material E strong with the stronger E, but rather because of the geometry. So what we've done is I've now given you an expression for the energy of beam bending. And what you see is that it's given by E times I. That's the joint parameter that gives you the overall mechanical strength, if you like, or the mechanical stiffness of the beam to bending, and then divided by the radius of curvature. The last point I want to make is that, in general, materials are not bent into arcs of circle. That seems like a very limiting assumption that we made. But in fact, it's not as limiting as you might think, and this is a beautiful aspect of differential geometry, and that is the fact that if I take some arbitrary geometry and a beam and I bend it into some configuration like you see here, in fact, at every point I can find a best circle. In other words, there's a circle that's the best circle for kissing that particular point on the beam. And so what I can do is I can pretend that each little slice has its own local value of R. And the consequence of that is that if I want to, for the general case, I want to write what the beam bending energy is, I can write it as this integral, which is I'm integrating along the arc length of 1 over R of S quantity squared. So this is the local curvature. In other words, what I'm saying is I'm going to parameterize how far I've walked along the beam with the parameter S. So this is the arc length parameter. It's simple. It's just you start at one end, and you want to tell me where to find you on the beam, you say you walk S steps. That's all. S is a parameterization of distance along the curve, and for every S there's a corresponding R, which is if you walk that far along the beam, you will find that the curvature, the circle that best fits that at that particular point, is R of S. And so now what I've done is I've said, well, then in that case, the strain energy is given by an integral where I integrate over all points on the beam with each having its own unique special R of S, which is its radius of curvature at that point. So what have we accomplished? We've accomplished that for a uniformly bent a circular beam, we found that the energy is given by E times I over 2R squared L. And for an arbitrarily bent beam, arbitrary state of beam bending, what we found is that the energy is given by EI over 2, and then integral 0 to L ds kappa of S squared, where kappa of S is 1 over R of S, and it's also equal to dr of S by ds. This is kind of like an advanced point if anybody cares, which is if I have the arc length parameterization, the curvature is given by the derivative of the position vector with respect to that arc length. So that's what I wanted to say. I apologize for the couple of glitches with my recording, but hopefully the essence of things was clarified.